Okay, in this video, we're going to discuss on heat. Okay, whereby this heat actually, what we already know, heat is something related to hot. Okay, so is how we describe how hot something is or how cold something is. Okay, so to measure this, usually we need to describe this physical properties. So the physical properties which could describe or gauge or quantify this hotness is what we call temperature. Okay, so in order to have a specific value or to quantify it much more in continuous way, we have a tool. Okay, in through the science progress, tools have been developed. So this tool, what we call a thermometer. So we have a thermometer as a tools. Thermometer. Although that this thermometer has so many ways of measuring, either you use uh, photo, either you use electrics or you use opticals or you use expansion. Okay, so what we're going to discuss more here a little bit, I'm going to just go right away on the common temperature thermometer tools, which is the mercury thermometer or something that is using or utilizing the expansion of a solid I don't know, of a material, okay, to gauge this heat hotness of something. Okay, so then there's a thermometer will give you a measurement, a physical measurement, what we call temperature. Okay, so in historical ways, as what because this measurement of temperature has been here since back in 90s, very in last century. Okay, so at that time, scientists around the globe has a different. It's very hard for them to discuss among each other. So that's why we are seeing a various of unit of measuring temperature. Okay, so the one that is much the one that is quite famous is Fahrenheit and Celsius. Okay, so let's see how this measurement is being utilized. Okay, so here we have three different sets of thermometer. So this is the purpose I show you this figure is to show you that the significant different or how this scale give us a different value, but we can have a, relative value for it, so that we know how does it work and how can we convert from one to another, because as what you know, this temperature is not decimals in as it went to one unit to another unit, as what we have done previously when we're dealing with prefix. Okay, like nanometer, kilometer, and so on, kilo, nano, micro, and milli, and so on. Okay, so here, if you what we have common, what we are already familiar with, is Celsius. Then, if you look closely here, uh, 100 Celsius to 0 degree Celsius. Okay, that one is what we common with is that at 0 degree Celsius, at 0 degree Celsius, we have the ice is freezing, start freezing, and then at 100 degrees Celsius, the water start boiling. So that is the reference that's the person who invented the Celsius aim for. Okay, and but for this person who do the Fahrenheit, okay, so his reference is that the 0 Fahrenheit is a water with a certain salt. Okay, so that's why it's a little bit below than the temperature described by the Celsius. Okay, So the starting point of 0 for Fahrenheit is slightly lower than the Celsius. Okay, and then if you notice this, where does the Fahrenheit lies at 100? So it should be somewhere here. Let's say just expecting somewhere here. So let's say this is 100 Fahrenheit. So the corresponding, if you do the conversion, the corresponding Fahrenheit, 100 degrees Fahrenheit is about 37.8. So this at this temperature, actually, they were thought that this is the normal temperature for a person. So the reference that been used for the Fahrenheit scale is that the 0 is for the freezing point of a salt water, okay, a certain mixture of salt water, and then the 100 would be the person normal temperature. So at that time, they measure it. Maybe there's a error there somehow. They measure it in terms of 37 point somewhere, 37.778. Okay, degrees Celsius. So this is the cause that the Fahrenheit and Celsius have a difference, 100 degrees and 0 degrees Fahrenheit and Celsius. Okay, then how can we convert to one another? Okay, so if you look at here, um, from then if we compare the 0 here, okay, and then the 0 here with the sorry. Okay, so then if we look onto the same range, okay, from here, from which means that if we look in terms of 0, we took the reference of Celsius here because that is the smallest one, and then we try to compare with the Fahrenheit. So which means that if I were to look from this height, from 0 Celsius, then we have 32 Fahrenheit roughly, and then we have it here, so 100 with 212 Fahrenheit, which means that what we have is 212 degree Fahrenheit, which is equivalent to 100 degrees Fahrenheit. Because the how this value increases, we could consider that the expansion is still linear. Okay, how these two temperature uh, measure, okay, linear. Okay, if you should know that this thermometer, there's a mercury thermometer, uh, has its limits. Okay, which means that it only could measure at a certain range, a certain height of expansion here, before after that the expansion will not be linear, which means it will not be corresponding to a certain level of expansion, the let's say 1 millimeter equivalent to 0.1 degrees Celsius. So as it goes beyond and further expand, it'll be less linear, which means that it will not be consistent anymore. Okay, so then that's why the accuracy is limited to a certain range of temperature only. Okay, so go back to here. So we have 212 Fahrenheit, degree Fahrenheit, which is equivalent to 100 degrees Celsius. And then another one, we have 32 degree Fahrenheit towards 0 degree Celsius. So understanding this will help you to remember how to convert the between these two. Okay, so note that, okay, that the Fahrenheit start with 32, and then the difference between this is 180. Okay, you see that if you plus 32 with 180 degree Fahrenheit, it will give you 212 Fahrenheit. So and then but the difference between 0 and 100, so this one is obvious, is 100. Okay, so so in this case we can use it in terms of fraction, but since that the Fahrenheit start earlier at 32 degree Fahrenheit at 0 degree Celsius, so we need to add up the thing. Okay, which means that let's say if I want to have 50 degrees C converted into Fahrenheit. So how can we calculate? So then the temperature in Fahrenheit would be 50, because this is the 50 which is from 0 to 50. So that 50 is actually the gap from 32 to 180, which means that like this, this is 32, this is 212, and then this is 0, this is 100 degrees. Okay, so this 50 is at the same expansion point, which means that it is at the same level there, only that the numbers is different. So then we just need to convert the numbers. Okay, so in a way that I'll show you here. So we just need to determine. So here the difference here is based on the value just now we get is 50, given is 50 degrees C. So we just need to determine what would be this value, not this value, which means the difference, the gap between these two. So the gap will reference to this degree C. Okay, degree Celsius is 50. So to know that gap, then we just need to using the this ratio, this this two ratio here. No, sorry, the ratio between. Let me just go back. Between these two. Okay. So then, if since that this is currently is in Celsius, so we divide by the gap of that Celsius, which is 100, and then the gap between the Fahrenheit, which is 180. Okay, so this one will only give us this value. So let's just calculate it first. So let me just simplify this one, that 180, so it can written that eventually it become more simpler than this. So this is 180 divided by 100. So if I were to divide by 20, that one will give me multiply by 9 over 5. Okay. So this one will give me 50 divided by 5 if 10 is 90 degree Fahrenheit. So remember, this is only the gap, okay, which means from here to this point only, which means this is only 90, okay, 90 degree Fahrenheit. That is the gap. Remember that we already started here, so this level is already 32 Fahrenheit. So then we need to actually add up 32 degree Fahrenheit. So then this will give us the exactly value for this. Okay, this will be 122 Fahrenheit. So that's how you do it. So in a way that the simplified equation would be temperature. We can write down temperature times 9 over 5 plus 32. So this, of course, this is temperature is in Celsius. Okay, in Celsius. Okay, so let's go to how we convert. So this is this one is from Celsius to Fahrenheit. So how can we convert the other way around? So the same thing, you just need to understand the concept of the gap here. Okay, so let's say if I were to have 122 to Fahrenheit. Okay, so at first I need to know. Okay, I need to know this is I want to convert into Celsius. Yeah, from Fahrenheit to Celsius. Okay, and then from here, so I got the 122. So I need to find the gap first. Again, I need to find the gap, that gap first, which will be 122 minus 32. Okay, remember, I need to find the gap first, so that's why we need to minus 122. with 32. 122 minus 32. So this will give us the gap. So which is this? In this case, this is 90 degree Fahrenheit difference between 32 and 122. After that, we we get the gap. Then we need to change that gap value to correspond to the scale of Celsius. So to do that, um, because this is in the Fahrenheit scale, so usually as what we do in the conversion method, as what we have done before. So this is Fahrenheit. So we need to cancel out the Fahrenheit part. So then we should have 180 because that's the total gap of this. Remember, just now this is the total gap of that. This is 180, and then the total gap of this, the same level between the two. This is 100. So then this one will be 180 because Fahrenheit, we're going to cancel the Fahrenheit, and then the top one will be 100. Okay, so then this equation will be simplified into, okay, let's just solve this one first. So 90 will multiply by 5 over 9. So then if you do this, you get again back 15 degrees Celsius. So to simplify this equation, so you have the T in Fahrenheit. So let me just write down here. Okay, so this equation can be simplified into this way. So you can have so this T will be in the Fahrenheit. So maybe I write down there. So this one also I should write down there C just to remind ourselves that this was Celsius. So this TF will be minus 32. So this one, all this thing will be fixed. Only the TF will be depend on that particular temperature that you are referring to. Okay, so the 32 is a constant value. Okay, then you multiply by, so that 100 over 80 can be simplified into 5 over 9. Okay, so yeah, that would be the equation. Okay, so what about Kelvin? So Kelvin, if you look at here, Kelvin, let's go back to this picture. Okay, if you look at the Kelvin, the difference between the 100 degrees Celsius and 0, if you minus this 37315 minus with 27315, that will also give you 100 degrees Celsius gap, 100 degree gap, 100 gap. Although the Kelvin does not use degree. Okay, so the Kelvin, a little bit of historical background on the Kelvin. So Kelvin it is an SI unit. Okay, it is an SI unit whereby the zero is the zero temperature of Kelvin is referring to the minimum possible temperature. So you cannot have a negative Celsius in the Kelvin. So Kelvin is determining the actual temperature, the what we call an absolute temperature, which means that this is the temperature that is directly refer to the energy of materials, because that is the energy of the material that give us the hotness. Okay, because of the vibration. So there's no negative vibration. The only whether there's a vibration or no vibration. So no vibration will lead to 0 Kelvin. So if you have slightly vibration, then of course it will increase the temperature. So Kelvin is the absolute temperature, which means that is corresponding right away to the physical properties of material. Okay, whereby the Celsius and the Fahrenheit, just now, if you remember that the 0 and the 100 was determined based on a certain reference, such as such as the solidifying of the water, okay, the freezing of the water, or in the boiling state of water, okay, or for the Fahrenheit is the freezing point for salt water, and the 100 degree Fahrenheit is referring to the normal body temperature. So that is their reference. Okay, so go back to the how we convert. Okay, so to make things easier right now, we need to look how Kelvin and Celsius is converted. Okay, since that the gap is the same, so we able to lose this part. Okay, the part that we need to change the scale. So since that the gap is the same, so then the scale also will be the same between the Celsius. This is for the Celsius. Between 0 and 100 also will give you 100-degree scale. Okay, so then the only difference that lies between the Celsius and Kelvin is that the Kelvin starts with 273.15 at 0 degree Celsius, which means that uh, if I want to convert into Kelvin, so let's say if I want to convert from Celsius to Kelvin, okay, such as if I want to, I give you a direct, obvious example here, such as I want to convert the 0 degree Celsius, 0 degree Celsius into Kelvin. So because we know that the Kelvin is 273.15 at 0 degree Kelvin, at 0 degree Celsius, so then the equation will be, so the temperature in Kelvin would be 0, just write down 0 there, 0 plus 273.15. Okay, so let's say if I will go to another example there, there's a written there 56.7. So if I were to put it 56.7, then plus 273.15, this will give you 15, this is 85, 3, so this is 9 to 3, 3 to 9. So roughly 330 Kelvin. So that's what you're seeing there. Okay, 56.7 corresponding to 330 Kelvin. So yeah, that's how we get this one as well. So in general, that the conversion between the Kelvin and Celsius will be like this. Okay, plus 273.15. So then if you want to convert, so this is quite easy. Uh, but later on you need to know how when you need to use it. Okay, okay. So if I want to convert from Fahrenheit into Kelvin, okay, Fahrenheit into Kelvin. So the process is similar to Fahrenheit to Celsius. Okay, so it's only that we need to add one thing, because if you notice that this only convert to Celsius. Okay, this one will only convert to Celsius, and then if you remember just now, let me just write down the equation just now. Oh yeah, already written there. Okay, so let's look closely. So this is the equation to convert from Celsius, uh, from Fahrenheit to Celsius. So if I want to convert from Fahrenheit to Kelvin, so what we get here is only Celsius. So what we are missing is only 273. So it is right away like this. So TK will be, so I just write it down. I just copy back all this, the thing I've written down just now. 32, 5/9. So this is Celsius. What I've written here is already Celsius. So that one is I need to add is 273.15. Okay. So this will give the equation for Kelvin too. Okay. So to wrap things up, Celsius to Fahrenheit. This one will be 9/5 TK TC plus 32. And then if you want to Fahrenheit to Celsius, it will be 9/5 TF minus 32. And then Celsius to Kelvin. So if you want to Kelvin to Celsius, we just minus instead of add. So I think that should be direct. So then this one should be TC plus 273.15. Then if you have Fahrenheit to Kelvin, just now is 9/5. You just follow out the how Fahrenheit to Celsius. Okay, TF 32. Okay, then you need to add another one is 273.15. Okay, and let me just add up in this side. So just to have everything complete. Okay, so Kelvin to Celsius is just right away Kelvin minus 273.15. That's why you might get negative value. So if you have a very a lower Kelvin value and lower than 273. Okay, and what about Kelvin to Fahrenheit? So Kelvin to Fahrenheit. So again, uh, so in order to Kelvin to Fahrenheit, you need to go to Kelvin to Celsius first, and then you go to the Celsius to Fahrenheit. Okay, so Kelvin to Celsius, what we get here is there. So we have TK minus 273.15. So all of this TK minus 273.15 is the Celsius. Okay, and then so I just put a column there, and then if you look at the Celsius to Fahrenheit, this one just multiply by 9/5 in front of it. So 9/5, just put 9/5 there, and then plus 32. Just as simple as that. So you technically just need to remember that the fraction and then understand. Just technically need to understand, and then the rest is just you need to polish a little bit of your mathematics. Okay. So as I mentioned before, that this temperature, all this temperature is linear. So you can view this that how does this absolute temperature is found. And although that we are absolutely haven't reached a 0 degree Celsius, 0 Kelvin yet, but we also it's quite close, huh? Basically about 0.00001 something. Okay, it's quite close, but still we haven't reached an absolute zero yet. Okay. Uh, so how can we know the existence of this absolute zero is whenever we plot a temperature versus pressure here, uh, what we're seeing here, numbers of data, okay? So as the pressure increase, you can see that the proportionality between the temperature and the pressure changes. Okay, a little bit changing. Somehow it becomes steeper and steeper. So then, from this data, what the scientists have done is that they try to extrapolate it, which led to 1 point. Okay, although that my drawing is not that good. Okay, this one should be a straight line. Okay, should be a straight line there. So in the end, it's merging into 1 point. So then, when the scientists calculate this, this is let's say we're using a degree 0 degree Celsius here as the center 0, and then what we obtain that that the temperature here is 273.15 roughly about that. Okay, you get at a point where the pressure, as well, you know, the pressure is you cannot have a negative pressure, although that there's certain cases that you might heard that the negative pressure that is a different kind of pressure. In other way, that the definition of pressure is something pushing. Okay, the reason that something pushing because something is actually inside a container or something. So if you don't have anything inside, so technically you won't get you don't have any pressure. So the reason you have like what you call a negative pressure is you have the pressure outside. Okay, but technically if I were to have in vacuum if I were at the vacuum space, and then I confine which means I empty the bucket there, or a container. So inside the container is a vacuum, outside also a vacuum. So technically there will be no pressure. Okay, but if you have in this world here, if you have a balloon being pumped, and then you inflate the balloon. Okay, so inside the balloon there's a pressure, but it remain that way, so in such a way that you can have if I were to increase the pressure outside, the the balloon can deflate. Yeah, it's not that the air is went out. Okay, let me just draw this one. Okay, so if you have a balloon, you inflate the balloon, so you have a pressure. Okay, so then the balloon inflate and become bigger and bigger. So let's say I stop, and then I put this balloon into a pressure container. Okay, then I increase the pressure outside. Then you will see that the balloon is become flat, as if the air went out from the balloon, which is not. At the moment, the pressure, the external pressure is removed, okay, or return back to the initial state. You will go back to this. You will inflate back. So it's not that the air that goes inside the balloon or went out the balloon as through this process, but uh, because of the net pressure that happen in the surface of the balloon. But so the one I want to emphasize is at this point, it's not there is no pressure. Okay, although that you can have the balloon is totally deflated. Okay, totally deflated, but the pressure is still there. Okay, because uh, it's only that the pressure outside and the inside is the same, so you don't see that the balloon is inflated anymore. Okay. Okay, so let's go to the heat. So heat is actually coming from a vibration. So it's heat can be in many forms. So you can have a radiation heat, you can have convection heat. Okay, so for convection heat is due to the uh, uh, flow of water or wind, but how does that is just how the heat is being uh, distributed, or how the heat is being delivered to one place to another. But the definition of heat itself is actually is a vibration of this molecule. Okay, as the molecule vibrate, so this vibrate is how this heat, what we so call heat, is being transferred to another. So you can have a very high kinetic molecule, and then we have one side to be at lower kinetic energy. And then when these two contact to each other, either through convection or conducting, okay, it will vibrate the cold structure as well. So then this one will slowly vibrating, thus it will reflect our measurement in temperature. Okay, that's technically how it goes. Okay, so then the if you see here is the heat flow is always from the high temperature to low temperature. Okay, that's the fact, because if you remember that if you have a molecule vibrating like this, okay, and then meet up with something that is less movement, eh, moving very much less, then you will see that these are the one that cause the slower molecular or substance moving to start vibrating more vigorously. Okay, so that's is only also another way to see it. Why does the heat energy flow from the high temperature to a lower temperature? So this is a low temperature, this is high temperature, vibrating at higher frequency, okay, high energy. So once transferred, the energy become part of the total energy molecule of the system. So which means that it still apply the conservation of energy. So it can result the internal energy change. Okay, so whenever this um, a substance here, so a system interact with a higher temperature body, so this vibrate, and then this vibration leads to vibration to a body. So then this body also going to uh, gain this internal energy. Okay, we will have its internal energy increase. So the unit of heat in this case is joule. Okay, joule or calorie. So this is joule or calorie. Okay, so what you have seen before that if I were to have a cup of coffee at 80 degrees Celsius, okay, and then I left the cup for a day at an environment of 25 degrees Celsius, then you will see, you observe that the cup is eventually become it will not be warm or hot, or neither it is cold. Okay, it is because the water, the coffee in the cup has reduced its temperature till it reached the same temperature as its surrounding. So if you have the same cup of coffee placed inside the fridge, where the fridge is at the 40 degrees Celsius, roughly about that. And after a while, you will realize that your coffee is also going to be very cold. And if you do actually measure the temperature, you will get that the temperature be about 4 degrees Celsius as well. So the phenomena that we are seeing here is that what we call a thermal equilibrium. So if we have a body such as this, and then this body actually consists of two different sets of body, and then presumably that this TA temperature is larger than TB. So as what we established before, the heat will flow from TA to TB, to B, from A object to B. So at the moment, okay, at the moment that the TA, I know TA reduce its temperature, and then eventually TB also increase its temperature. TA it reduce its initial temperature, but TB actually increase and due to encountering an increase of internal energy does increase in temperature, which eventually led to an equivalent temperature of TA equal to TB. So at this time, it's not that there is no heat transfer at all. There are heat transfer. There's still a process of heat transfer. Only that the amount of heat transfer from A is about the same of amount of heat transfer towards B. Presumably that uh, okay, there's no surrounding loss. Okay. Okay, so at that time, when then the same amount of heat transfer from A is equivalent to the amount of heat transfer from B to A, that one is when what we call there's no net heat exchange. It's not that there's no heat exchange, it's only that there's no net heat exchange. So that is when the state what we call a thermal equilibrium. Okay. Okay. So next one is that okay, and as what you know, whenever we heat up something, and then this that thing will remain hot until further, and then you realize that that thing there might be two possible things, okay, and when you heat up a cup of water, only a few minutes, the cup water is already lukewarm, and then eventually become at the same room temperature. But when you heat up a full bucket of water, maybe in a pot, using pot, you heat up water, then you realize that it took a little longer for it to actually cool down. Okay, so and then another way to see it is that whenever you try to heat water, okay, you realize that it increasing its temperature slower compared to oil, maybe oil. Okay, so this kind of property actually can be observed. It's also can be observed. It's been described to what we call a heat capacity. Okay, whereby whenever we will supply heat, okay, supply heat to water. So the heat we call here the source of heat is Q. It can be from direct burning candles or Bunsen, or it can also coming from heating coil. Okay, it doesn't matter, but we describe it as a heat energy. Okay, so that what we call we give it in terms of Q here. Okay, the symbols. Okay, and and then you realize that uh, let's say you quantify the amount of heat. Okay, let's say you give because I just now already given you the joules. The definition of joule is the heat is being can be quantified in terms of joules. So let's say we know we quantify the amount of heat that, and then we try to control all the heat went through this liquid, whatever liquid that is. So presumably, let's say we go to 200 joules, and then we realize that that liquid increase the temperature increase by, let's say in this case is 20 degrees Celsius, which means that this increase, the increase in temperature, del T there, which means the final temperature minus initial. Let's say initially the temperature is 20 degrees Celsius. So when I put delta T here, 20 degrees Celsius, which means the final temperature here should be 20 degrees Celsius plus 20 degrees Celsius, whereby this is the initial temperature plus delta T. Or you can say that um, at this delta T actually equivalent to, this is 40 degrees Celsius, that's the final temperature. Or delta T is actually final temperature minus initial temperature. Okay, then this will give you 20 degrees Celsius. So that's what I mean by delta T is equivalent to 20 degrees Celsius. Okay, then starting from the same back, let's say we go back to 20 degrees Celsius, and then we increase the amount here into 400 joules. And then you realize that the delta is increased by 40 degrees Celsius. The change, which means that the final temperature here should be 60 degrees Celsius. Okay, the initial temperature plus the change on temperature that will give the current temperature. Okay, so so in this case, you will see that there's a proportionality. Okay, the proportionality is such as that as Q increase, the change of temperature also increase. Okay, so then you can see that this proportionality, such as I don't want to make a line, so it's like a straight line. So it's a direct proportionality. Okay, you increase Q, you increase delta T. You increase Q even further, you increase further delta T also until just before it change phase. Okay, so from here we can make into equation. We just put a constant delta T. So then the question here, what is constants mean? So this constant mean is that is Q over delta T. So again, what does this tells us? Okay, this tells us about that the amount of heat, okay, this C represent the amount of heat required per temperature. Okay, so you can have different sets of material where we have the different sets of C. So let's say this is Q, and then this is delta T. Okay, not T, this is delta T, is the amount of change, it's not the current temperature. Okay, because heat is not permanently there. It can have it and you can remove it. It's not belong to that properties. And then temperature just responds to the amount of heat that went through the body or leave that particular body. So then here we can have a multiple gradient which give you different sets of C. So from here you can see that let's say uh, one material where we have high C, high value of C, means that it required more heat just to increase one temperature. Okay, a single temperature. Okay, whenever you increase C, then you will see that, let's say we just focus on Q, you increase the C, that means that Q have to increase, or you can have a choice that the same amount of Q led to a smaller. Okay, you can have either in terms of this higher C, higher Q, or you can also look in terms of higher C, lower T. So let's go one by one. So let's say for this first case, you can say that higher heat capacity. So I just want to right away again, this is constant is what we call the heat capacity. So higher heat capacity also means that you require more energy to increase 1 Celsius. Or you can have another way to say it, that you with one, let's say with 100 joules, okay, you increase uh, less than 1 Celsius. Sorry, 1 Celsius. So you mean that with the same amount of energy, you will have a lower increase in temperature. Okay, let's say this heat capacity is higher, you at the same amount of energy, the temperature increases less for things that have high heat capacity. Or you can say that with high heat capacity, you will need more energy to increase 1 degree Celsius or 1 degree Kelvin. Okay, remember, whenever this is the equation Q equal to C delta T. So remember that whenever we're dealing with equation, we need to use SI unit. So there's no it is not exceptional for temperature as well. So the SI unit is Kelvin. Remember Kelvin. So in this case, just now I use Celsius. In this case, it is okay for you to use Celsius. You be still safe. It is because of that. This is not decimal. That's one thing. And then if you look at here, if I were to have change in temperature, such as from let's say from give me about this number, let's say 50 degrees Celsius, the change of the 50 degrees Celsius minus 10 degrees Celsius. So if I were to convert this thing into Kelvin, so 273, then this one gives 3 to 273, 3 to 3.15. Okay, 15. Okay, and then this one minus 2, 8, 3.15. Then if you minus these two, it still give you 40 degrees Celsius. This is the same thing. Okay, it's the same thing. So in this case, this is in Celsius. This one is in Kelvin. Okay, so both of them are still going to give you the same amount of uh, C. Okay, so this is C is a heat capacity. Heat capacity. So know that the heat capacity also depend on the quantity. Okay, it's also as I mentioned just now, a cup of water will heat up much more faster than a pot of water. Okay, but you can have it another way that um, how is it? Maybe the oil is will heat up much more faster or with the same amount of heat. The oil will become hotter compared to when you boiling water. Okay, so it's depend on two things. It's not just mass, the quantity of mass, but it's also depend on the types of materials. So then, to avoid this confusion, comparing between the two different, let's say I will comparing this amount of water with this amount of oil. So this is unfair or uncontrolled comparison. So we should actually compare between the same. Okay, we should compare with the same. Yeah. Okay, we should compare with the same amount of quantity. Okay, so when we compare the same amount, then we able to remove the dependency of the mass. So then this will give us under different constant. So we manage to break this constant up to get a different value. So this is specific. No, this is heat capacity. C, the big C, capital C. Heat capacity. So then what we know just now, the heat capacity also depend on mass and also to depend on the material. So this is a small c. So then it will give us that the small c is equivalent to big C divided by m. So then this C is what we call a specific heat capacity. So then this equation Q can be written as, because just now I write down here is big C, this is capital C. So this one should be not capital anymore, is Cm del T. Okay, so the unit will be different. Okay, so what you'll be doing to know the unit, just rearrange this equation Q m del T. So then you can have this joule over kilogram. Then this is temperature in Kelvin. Okay, negative one. Also, although that the temperature can be in Celsius as well. Okay, so let's do a little bit of example here. See what we have known. Just now we already know about heat, and then we know about how this heat can be transferred to one another, and then how this transfer would stop at the moment the temperature of these two materials is the same, where what we call is thermal equilibrium, and then we also know that the temperature increase, the temperature change is dependent on how much heat that's been transferred to that material, and then it's also depend on the types of material which given by the specific heat capacity. So let's say we go to a certain case that we have water, okay, and then I have a hot rock, hot marbles here, and then I put it, let's say the hot marbles is about 80 degrees Celsius. So then I put it inside this water. So let's say the water is only about 20 degrees Celsius. So I think you're going to expect that you should expect that the water will increase in temperature, and then the marble will cool down a little bit. So then the temperature will be somewhere in between. So how can we calculate this? Okay, so so that temperature is when the temperature reach or these two materials reach what we call a thermal equilibrium. So we know already that the Q is could be given by mc del T, okay, whereby this heat is energy. It's been given by the mass of that any object, and then the specific heat capacity of that object, and then how much the temperature change. What does it mean there? Whenever, let's say, we have a cup of coffee here, 80 degrees C. Let's say the mass is about 5 gram. Okay, so this is 80, 5 gram, and then let's say this heat capacity is 1 joule kilogram per kilogram per Kelvin, and then presumably that the water eventually drops to 20 degrees Celsius. Then our question is that what how many energy is lost to the surrounding. Okay, so then you can just use this equation. Okay, you put the m there is 0.005, and the specific is 1, and then you have the change in temperature is 60. Okay, so this one will give you roughly about 0.3 joules. So from here you know that through this process, that from 80 degrees Celsius to 20 degrees Celsius, the heat decreases into 0.3 joules. Okay, which means that the water lost its heat uh, to 0.3 joules with no an equivalent amount of 0.3 joule. When the when the coffee here cool down from 80 degrees to 20 degrees, which means that 0.3 joules of heat has been dissipated or lost to the surrounding. Okay, so what happened here? Yeah, we're going to use the same thing. Okay, initially this one have its own energy. Okay, this one also have its energy. Okay, so the process can be two ways. Okay, you can have it another way. I can have it the other way around. So if a coffee here from 20 degrees C and then heat up into 80 degrees C, it means that a 0.3 joules, the same equation form, the same equation, you can say that 0.3 joule are going to this to the coffee. But this one in the top part here is the 0.3 joule is leaving the coffee, thus decreasing temperature. So you can have it either way. Okay, so this Q can be an energy goes inside or energy goes outside. Okay. Okay, so so here when we're dealing with two or three things, we can apply what we have just now. So what are the uh, concept that we need to take account so that we can solve this problem? Because we know that the Q here will leave and then enter the water here, and then the water will receive that heat and then increase its temperature. So what are the things that constant here? Okay, if you remember that before we already went to conservation of energy. So the same thing here, the total energy will always be the same. So which means that the total energy chain will not be the total energy chain will not change because it's conservation of energy and presumably it's not lost to the surrounding. So the total energy, which means the total energy, the energy from here and the energy from here, from the water and the marbles should be the same. So which means that the E total here will be equivalent to Q. Let's say I put it, this one is A and then this one is B. So QA plus QB will always have to be equal to zero, which means that the total energy, whatever it is, whatever the situation is, the total energy for any uh, object, okay, within this closed system, okay, which means that there's no energy leak out from the system. That's why we call it a closed system. Will always not changing. Okay, it will always the same. The only thing change is that the distribution. Some of the energy went to B, and then some of the energy been absorbed is lost from A. Okay, only the distribution. Okay, so from here we can get that QA equivalent to negative QB. So then you can solve the temperature from here. Okay, so then you just need to input the value respectively. Then you have MA, CA, del dA minus, don't forget the minus there, MB, CB, del TB. Okay, so then if I were to break it down, MACA, so this one will be TAF minus TA initial minus MBCB TB final minus TB initial. Okay, so as I mentioned just now, the final temperature will be is when both of them reach thermal equilibrium. As what you know just now, thermal equilibrium mean that TA here for this case is equivalent to TB. So when does TA will be equivalent to TB? It is when both of them at the final stage. So then here we can have that one of this change into TAF or TEBF, doesn't matter. Just to make sure that you have actually one constant. So rearrange this thing, you will obtain TAF, which also equivalent to TBF, which this is the equilibrium temperature.